All right, in this lesson we're going to be talking about how do you interpret correlation coefficient. So by this time you should have calculated the correlation coefficient for the 3 homework problems, as well as created some scatter plots and kind of looked at the pictures worth 1,000 words, and then actually also calculated those correlation coefficients. So what we're going to be talking about in this lesson is how to interpret R. The first thing you really need to grasp hold of with regard to interpreting R is that correlation does not imply causation. That's something that is, I would say, quite misunderstood often. People think that if two things are associated, and let's just say that they're positively associated, that one causes the other. And again, that's not necessarily the case. As an example, if teacher enthusiasm is our X variable, and it is found to be positively related to student achievement, it would be easy to say that X caused Y, that teacher enthusiasm caused greater student achievement. But here's an example where two things are highly correlated, and you can tell me if you think that they cause each other. And this is a factual relationship, but it has been found that the number of churches in a community is the X variable, has been found to be related to the incidence of violent crimes, Y. Not WHY, but that's the Y variable. So how would you interpret that correlation? Does churches cause violent behavior? And if you haven't figured it out, that's what the little clip art is supposed to be, violent behavior in churches. Here's another one that might seem kind of odd. It's been demonstrated that as people age, which is the X variable, the number of doctor visits actually increases. And that's the Y variable, number of doctor visits. So does age cause doctor visits? Not necessarily. And what that implies too, though, is that there are outside variables that are not taken into consideration if we're talking about churches and violent crime, or if we're talking about age and doctor visits. We probably all can guess that as people age, the item that increases their number of doctor visits is number of illnesses. So another thing that we need to think about in terms of interpreting R is significance or statistical significance. For now, just know that we can do hypothesis testing or significance testing for our correlation coefficient. And if we do, we are answering the question, is the correlation significantly different from 0? And there might be instances where that is something that we are interested in. I guess a third interpretation is something called effect size. We're not really well schooled on what statistical significance means, but suffice it to say right now, most of what you read in journal articles are the situations where researchers have found statistical significance between variables. And so statistical significance is important in research, but sometimes it's not the only thing that is important. And so effect size is related to what would be considered practical significance. And the way that you would interpret effect size is that the correlation coefficient itself is a measure of effect size or practical significance. So if R is 0.10, that would indicate a small effect size. R is equal to 0.30 would indicate a medium effect size, and R is equal to 0.50 would indicate a large effect size. We'll talk a little bit more about effect sizes when we do some of our hypothesis testing. And then a couple other ways that we'll talk about that you can interpret R is, number one, just looked at directionality. So is there a positive or a negative correlation between the variables that you're interested in? And then nextly, we can interpret R by looking at the absolute value of R. And we've mentioned this, I think, a little bit, because that the or maybe we haven't, but the absolute value of R is related to this actual strength of association. So think back to our scatter plots. Uh, the closer those data points were together, the more or the higher the relationship would be between X and Y. So this came from an author from a textbook that I've used for several years, and it's just some words that you can put with what is the actual value of the absolute value of R. So anything that is over zero point 0.8 up to up to 1.0 is considered a very strong relationship. 0.6 to 0.79 is considered a strong relationship. 0.4 to 0.59, a moderate relationship. 0.2 to 0.39, a weak relationship. 0.01 to 0.19, a very weak relationship. And R of 0 is no relationship. So let's look at a couple of examples. And the first one that let's talk about is, let's say we're looking at height and weight, and R is equal to 0.82. So the interpretation of that would be that there is a very strong direct or a very strong positive relationship between height and weight. When you're interpreting the homework, I do want you to use both directionality as well as the terms that you see on this slide: very strong, moderate, weak, very weak relationship when interpreting. And then you're also going to interpret the effect size. So another one let's look at would be as hours practicing golf go up, golf score goes down. And let's say that the correlation between those two is a minus 0.52. So the interpretation there would be that there is a moderate inverse relationship between hours practicing golf and golf score. So again, you have to think about the absolute value of R as well as directionality. Now these last two interpretations are kind of interesting. The first one is something called the coefficient of determination, and you can see the symbol there is R squared. And then you can see a graphical display down here at the bottom. By definition, the coefficient of determination is the percentage of variance in one variable that is accounted for by knowing the variance in the other variable. This is called the explained variability. Mathematically, it is literally you take your R and you square it. So we have an example here. If hours studied is our Y variable, if Y is GPA, and the correlation between those two is 0.70, then our R squared is 0.70 times 0.70, which gives us 0.49. And the way that you would interpret that is 49% of the variability in someone's GPA can be accounted for by knowing how many hours that they studied. And what I want to talk a little bit about is, I'm going to go on and hit this next button, and just that you can see that there's a graphical representation. In this graphical representation, typically we're going to put our X as the left-hand variable and our Y as the right-hand variable. And if you can think back to when we were introducing X and Y here, we defined X as our independent variable, and we also said that one way it typically is interpreted is it's the one that chronologically comes first, and then our Y variable is our dependent variable, and it is the variable that typically comes second chronologically. And so here's a good example where hours studied would be the thing that you would think would come before you found a GPA. When we interpret the coefficient of determination, I want you to always interpret it in terms of your Y variable. So you'll know what that is when you're given data by me, but always interpret it in terms of the y variable. So again, the interpretation here is 49% of the variability in someone's GPA can be accounted for by knowing how many hours that they studied. Notice that that is a percentage. So when we think about R, in this case, R is equal to 0.70. Even though that is a number that is below 1, it is not a percentage, but R squared is a percentage. And then most specifically, from a graphical standpoint, it is the overlap in our Venn diagram. So it is the explained variability. We can explain 49% of someone's GPA if we know how many hours that they study. So that's the coefficient of determination. And then I think I have a haha here. I'm sorry, Cornelius, but I just don't see us ever becoming a Venn diagram. And notice he's got a tear coming out of his eye. Okay, lastly, we're going to talk about something called the coefficient of non-determination. This is the percentage of variance in one variable that cannot be accounted for by knowing the variance in the other variable. So again, I'm going to jump down here to the graphic display. This will be our x, this will be our y. This is related to, or it's called the unexplained variability. We're going to make this, again, in terms of our y variable. And mathematically, it is literally calculated by squaring r and subtracting that from 1. So in the same example, if x is our hours studied, y is our GPA, and r is equal to 0.7, 1 minus r squared is 1 minus 0.49, which in this case yields a 51. And again, that is the 51%. So here is r squared, and here is 1 minus r squared. So it's the variability in someone's GPA that we can't explain by knowing how many hours that they actually study. Now what you're going to do is go back to the homework and complete step 2 of correlation 1, correlation 2, correlation 3, and that is going to require that you do some interpretation of the correlation coefficients that you've actually already calculated.